All right, hey. So we're gonna do a quiz Friday on cones and cylinders. So let's go over these practice problems. Um, a lot of these problems I've done already in class, so I'm just gonna do them all anyway, so you guys have them. But of course, fast forward, just skip ahead to whatever problems you actually need. But looking here for 18, it says a conical tank full of water is 20 meters high and 10 meters in diameter at the top. If the water is flowing out at the bottom at a rate of 2 cubic meters per minute, find the rate at which the water level is changing when the water level is 16 meters above the bottom and when the water level is 2 meters above the bottom. If you can do part A, you can do part B. There's no real difference between those two things. Um, but let's start the way I usually like to start, which is let's kind of gather all the values that we know. We know that the formula for the volume of a cone is 1/3 pi r squared times height. So we know there's typically going to be a volume, a radius, and a height at play. And then there'll be the rates of change for all three of those things. dv dt, dr dt, dh dt. And as we read through the problem, usually a lot of these jump out at us. So it says the conical tank full of water is 20 meters high. You might be tempted to write down that makes our height 20, but you would be wrong because this doesn't say the water. This just says there's a conical tank. So this is like some vessel made out of like metal, and inside of that there's water. Oh rats, that was supposed to be blue. Okay, I'll make that blue. So be careful, because sometimes you're given the dimensions of just the tank that holds the water, and what you actually need is the dimensions of the water. So notice that when they say those dimensions, it might not actually refer to what we care about. So I'm going to go ahead and skip right past that and keep reading instead. The 10 meters in diameter at the top is also referring to the tank, not the water. So it says if the water is flowing out of the bottom at a rate of 2 cubic meters per minute, okay, that really is dv dt. And it's flowing out, so we're losing volume. So this is negative 2 cubic meters per minute. It says find the rate at which the water level is changing. Water level is the height of the water, so that means dh dt is going to be the answer to the question once we solve. It also says when the water level is 16 meters above the bottom. So that now is actually a measure of the height of the water. The 16 is the number we actually care about. So that's 16. So as I look at this, I can see that R is still missing, dr dt is still missing, V is still missing. The 20 and the 10 like have nothing to do with the problem. This 2 is only useful for part B. So there's all sorts of mess going on here. So what's the deal? Well, one thing to remember is immediately if I were to differentiate this, even if I wasn't going to replace R with an H or H with an R, when I differentiate V, it's gone. You end up with dv dt. So I think I can actually say pretty much 100% of the time that we never need to know the volume. Now sometimes they give us the volume, but they only give us the volume so that we can use it to solve for the radius when we need the radius. Or they'll give us the volume and the radius so that we can solve for the height when we need to know the height. But 9 times out of 10, 99 times out of 100, I don't think we're going to need the volume, so that can go. And also, I'm not really sweating the fact that I don't have R or dr dt, because I'm going to want to replace R here with an expression containing H. This is what we've been doing for the cone problems, is we just make sure that instead of an equation that involves both R and H, we replace one with an expression in terms of the other, so that we either have all R's or all H's. And since I don't have information about R, and since I don't have information about dr dt either, it's pretty clear that we're going to want to go for replacing R with something involving H. And so how do I do that? Well, that's where this first sentence came in. They said that in our tank is 20 meters high all the time. And our tank has a diameter of 10 all the time. Now I don't care about the diameter, so I should probably immediately convert that to the radius. And notice that that's 5. And we said the big trick to these cone problems was, okay, let's set up a proportion again. because we know that the cone-shaped water and the cone-shaped tank, they will always be similar to each other. So we've got this idea of proportionality again. So we know that the height divided by the radius is always equal to the height divided by the radius. So for the water, for the tank, height divided by radius should always equal height divided by radius. So I'll do the variables h and r for the water, then I'll do the actual numerical values h and r for the tank. So my height is 20 when my radius is 5. That means that suddenly I can cross-reduce and come up with an expression for r. So I cross-reduce and I get 5 h's equals 20 r's. Now I want to solve for r because I want to plug into r to make the r go away. So divide by 20, and I see that 1/4 of h is r. And my weird little tablet again is being kind of annoying. When I try to draw 4s, it connects them at the top and can make them look like 9s. So again, if you ever see that, if you think you're looking at a 9 that you think ought to be a 4, it might just be because my tablet went haywire. Anyway, where are we? I think we just said that back to this original volume equation, we're not going to differentiate yet. You're jumping the gun if you try to do that. Before you differentiate, you're going to want to get rid of the r by replacing it with an expression that equals h. And we just found that expression over here by setting up this proportion. So we now know that r is equal to 1/4 of h, so I'll plug that in. 1/4 h goes here. Now I don't have an r anymore. I do just have a bunch of h's. So I'll clean this up now. And this does not ring a bell, but I don't think I've made a mistake. So this makes what? 1/16 times a third would be 1/48 times pi. And then I'd have an h squared times an h for an h cubed, and this all still equals v. So I now have this simplified version over here in, what is this color? Let's call it hunter green. So we started out up here in maroon, and that was no good for us because we had both an r and an h. So we substituted into this red equation. Now we don't have r anymore, we only have h. Now we're nice and simplified. So it's time now to differentiate. So we'll take the derivative with respect to time, and we'll get dv dt. We will treat this whole mess here like a coefficient, and we'll just multiply by 3. So we get 3/48, which is basically just right back to 1/16. Then a pi. Then the h that was cubed is now an h that is squared. And we also chain rule out a factor of dh dt. And now we can substitute in and solve. We know from back in the beginning of the problem when we were planning everything out that we were trying to solve for dh dt. So we know that guy's our variable, which means we know dv dt, it's -2, because they told us the water was flowing out at that rate. We've got a 1/16, we've got a pi, we've got the height, it's 16. So we square the 16 and we get dh dt. And I remember this answer now. So now the easiest thing in the world here would be to immediately notice that if this is over 1 and this is over 1, then we could just cancel one of these 16s with one of these 16s. So we're looking at a -2 that equals 16 pi dh dt. So to solve for dh dt, just divide both sides by 16 pi, and that'll land you on -2 divided by 16 pi, which will quickly reduce down to -1 over 8 pi, which of course is approximately equal to, let's hit the buttons on our calculator here, 1 divided by parentheses 8 pi. Remember, you got to put that denominator in parentheses or else it comes out wrong. So I'm getting -0.0398. And unfortunately that 8 and the 9 just went behind my face. So let me get them back. Sure, we'll just move everything. Alright, but there's your answer. Please remember, somehow there were still actually people who forgot or just never understood that I'm ordering you to give me two answers. You must give me the exact answer that still involves pi or radicals or fractions or whatever it takes for your answer to be an exact expression. I need that. And then I also want the rounded off decimal. And of course I also want units. So I drew my little box here prematurely. Now this is volume, and volume is always measured in cubic units. So if you go back up to the problem, let's see what we're working with. So it says meters here. So these must be cubic meters. Also, there was a rate of change given to us somewhere, right here, the 2 cubic meters per minute. I'm screwing up, aren't I? Because we didn't just solve for a volume. We just found dH/dt. That's not a volume. That's a unit of length. So these would not be cubic meters. These will be plain old meters. But it'll be meters per minute, since it's a rate of change. So meters per minute is the final thing. So essentially just tell yourself, your answer to me better have 3 things in it. I better have an exact expression, a rounded decimal, and appropriate units, whether it's meters, square meters, cubic meters, meters per minute, square meters per minute, or cubic meters per minute. Make sure you pick the right one, okay? Because that's worth kind of a significant amount of credit, in my opinion, is having the right units. All right, that's it. I'm not going to bother doing part B because I'm hoping that it's obvious to you that the only thing that changes here is that suddenly our height is equal to 2. So in the part right here, where we went from the blue to the red, you're just substituting in a 2 where we substituted in a 16. So you get a different answer, but who cares? It's not useful to talk about, in my opinion. So let's just go to 19. On we go. All right, this guy says sand is being poured onto a conical pile at a rate of 9 cubic meters per minute. Friction forces in the sand are such that the slope of the sides of the conical pile is always 2 to 3. How fast is the altitude changing when the radius of the base of the pile is 6 meters? So this question is kind of the same as the last one. In the last question we had a container that was holding water. So as the water changed and as the level went down, 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 of course all these cones, of water were similar to each other. This time kind of the exact opposite's happening. You have sand spilling out, so you get a small little conical pile at first. Then more sand spills on top and it grows to be a bigger pile of sand. And then you put more sand and it grows to be a bigger pile of sand. And again, what we need here, this whole thing only works if these piles of sand are similar. So I don't know how much of a chance you guys have had to play at the beach or something, but if you use like wet sand, then there'd be a greater force of friction, and suddenly if you just put more sand on top, it might just go burp and just build up higher and higher. And then those cones are not similar to each other, so we would lose the ability to do what we did in the previous problem, where we were able to just express R in terms of H. We were able to do that because the cones were similar. So that's why this part here, where it says the slope of the sides of the conical pile is always 2/3, that's their fancy way of saying that the cone is growing in such a way that every resulting cone is similar to the previous cone. And that's going to allow us to do this problem the same way we did the last one. So let's go through this a little more. Draw yourself a cone. And what the heck does it mean for the slope of our sides to be 2/3? Well, doesn't a slope of 2/3 mean you've risen 2 and run 3? So I went up by 2 and I only went over by 3. So that's kind of a gentle slope, a slope that's less than 1. The angle it forms with the horizontal is less than 45 degrees. So we should be expecting a cone that goes burp, burp, and is wider at the bottom than it is tall. And that's the exact key here, is we're looking for that relationship between our height and our radius. And we can now see that our height divided by our radius, that ratio, is that we've risen 2 and run 3. So our height is 2, but our radius is 3. So we can see that that height to radius ratio is 2 to 3, which means if I cross multiply to get a 3h, that equals a 2r, then I can either solve for r by dividing by 2. I get 3 over 2h equals r. But I could also divide by 3 to figure out that h is equal to 2/3 of r. Because honestly, at this point, I'm not sure which one I want. Sometimes we want to plug in for r to have an equation that only contains h. sometimes you plug in for h to have an equation that only contains r. So let's go back to the problem now, actually read it, figure out which one of those we want to do. And again, I would do this by just making a list of all the variables that are important to us, and that means volume and radius and height and dv dt and dr dt and dh dt. And again, it's pretty safe to assume that the volume is not going to matter to us because we're going to differentiate that away. But it says sand is being poured at the rate of 9 cubic meters per minute. That sounds like the rate of change of my volume. And we're gaining that much, so it is positive 9. The 2/3 is not any of this. The 2/3 just gave us that relationship between the similar cones. It says how fast is the altitude changing? That means dh dt is what we're solving for. When the radius of the base of the pile is 6 meters. All right, so that makes this a little bit tricky because suddenly now I've got the radius but not the dr dt to go with it. And I've got, and I want to find dh dt, but I don't have the height to go with it. We kind of need these guys to go together because if I was to rewrite my equation in terms of h's only, then when I differentiate, I would have h and I would also have dh dt. I would kind of need to know both. If I wrote everything in terms of r, I would have r and dr dt. I kind of need both. So this question is, well, actually it's a little different from the last one because this time I need to use the radius I was given to find the height. And number 18, we were happy with everything they gave us. We had the height and we needed the height. But this time we have the radius and we need the height. But hey, don't forget, it was like 5 seconds ago that we came up with these conversion factors. So if you know the radius is 6, can't you just plug into the second equation right here and say that my height will always be 2/3 of my radius? And 2/3 of 6 is 12/3, aka 4. So giving us the radius is basically just as good as giving us the height, because all we have to do is solve this little baby math problem that we already worked out anyway, to figure out that the height is 4. Which means I now know that I don't care about the radius and I don't care about the rate of change of the radius, because what I'm after is, again, dh dt. I'm looking for the rate of change of the altitude. So starting now, this problem is going to feel just like the last one, because we go volume equals 1/3 pi r squared h. And again, we immediately want to get rid of that r. So instead of r squared, we'll use our similarity ratio that we came up with, where we found out that r was equal to 3/2 of h, and we'll substitute that in. And then we'll simplify this expression down. This is now, what, 9/4 times 3 makes 9/12 times pi times h squared times h, so h cubed. And so there's our new equation. The only thing I don't like about it is, of course, 9/12 reduces. So make sure you reduce that. That'll actually be 3/4. Yoink. But now that we've rewritten and simplified our expression, we can go ahead and differentiate it. And there's that 4 problem again, where it tries to make it look like a 9. And that was yellow. I don't know if you can tell that's yellow, but whatever. All right, so we differentiate, we get dv dt. And it equals, well, we multiply by 3, so we get 9/4 times pi times an h that is no longer cubed but squared, and then we chain rule out a dh dt. So up here in blue was our sort of original volume equation. Now we're differentiating it, so here we are in green. And now we just substitute. They told us dv dt was 9, so we'll substitute 9. Then we got this 9/4. We've got this factor of pi. H we figured out. We used the fact that the radius was 6 to figure out that h had to be 4. So in goes 4, it's squared. And then dh dt is our variable. So, all right, again, it should be sort of obvious that this 1/4 in my denominator will cancel one of these 4's. So you're now just looking at 36 pi as your coefficient. So divide by that 36 pi, and you get 9/36 pi. which of course reduces by a factor of 9, so you get 1 over 4 pi now instead. That, by the way, is our final and best answer. So if I go to the calculator, I can do 1 divided by 4 pi. And that'll be 0.0796. And this is the rate of change of the height again, so it's not going to be cubic meters, it'll just be plain old meters. But it is a rate of change, so it'll be meters over time, and time here is minutes. Sometimes it's seconds, sometimes it's hours. This one happens to be minutes. So there you go. There's the final answer to that one. And with 2 problems behind us, and the fact that it took 21 minutes means I'm going to try to go faster now. Hopefully you guys have caught on to the basics here, so maybe I can go a little quicker. Alright, so 20. This one says sand is leaking out of a hole in a container, and it forms a conical pile whose altitude is always the same as its radius. Okay, altitude is the same as its radius. That sounds like that might be the easiest similarity ratio yet, because we know now that height divided by radius will always just give 1 over 1, right? If they're the same, then the ratio is 1 to 1. And so cross multiplying tells you that h is just literally equal to r. We can just replace one with the other. So with that in mind, what else do we know? It says the height of the pile is increasing at a rate of 6 inches per minute. That seems to mean that dh dt is 6. It says find the rate at which the volume of sand is changing. So it looks like dv dt is the thing we want to solve for. And it says find the rate at which the sand is changing when the altitude is 10. So they're giving us the height, telling us it's 10. So again, they're sending pretty strong vibes that r and dr dt can just go to he double hockey sticks, which means that if we take our formula, 1/3 pi r squared h, then again we just want to kill off r. Now this is 3 problems in a row where we're making r go away. Hopefully you guys are all understanding that of course there might be a time when you would want to turn h into r to have 1/3 pi times r cubed and solve from there. But again, because we were given information about h and dh dt, we obviously want to leave this in terms of h. So again, we take our world's easiest conversion factor where r is just literally equal to h, and we get h squared times h, so this is h cubed. And there we are. We're immediately sort of simplified and ready to differentiate, so we do. We get dv dt equals 3 times 1/3 is 1, so this will just be pi times h squared times your dh dt. And then you substitute in. dv dt is what we are hoping to find, so leave that alone. That's your variable. Pi is pi. H is known to be the height, so that's 10. And dh dt is known to be 6. Yeah, that's everything. So dv dt is 600 pi. And at this point, I guess I'd say, hey, hang on a second. Is it 600 pi or should it be negative 600 pi? Did I miss anything? But we didn't. Or maybe we did. It does say here that sand is leaking out. So doesn't that mean we're losing volume? Well, no. Pay attention to the problem. They're saying they've got some big old like bucket. I don't know. Maybe it's a box. And the sand is leaking out of the box. So yeah, the box is losing volume, but then it's forming a conical pile down here. So the cone is gaining that volume. So even though this question is sort of framed as we're leaking out sand, well, we're leaking sand from a container that we don't care about, which means the thing that we do care about is gaining. So that should certainly be a positive rate of change, in my opinion. Yeah, because it says find. This was the one that we talked about in class as being a little ambiguous. It says find the rate at which the volume of sand is changing. They should probably say find the rate at which the volume of sand in the conical pile is changing. Or they could say, find the rate at which the volume of sand in the container is changing. If they referred back to the container, then you would want to say negative 600 pi, because the container is losing sand. But if they specifically said, find the rate at which the volume of sand in the cone is changing, then the cone is gaining, and it would have to be positive. This question's a little bit bad in that regard because it's not clear whether they want you to be losing volume from the container or gaining it in the cone. But on the quiz, I'll make sure that nothing is ambiguous. I'll make sure that it is clear that the rate of change I want is the one for one or the other. Okay, anyway, what's 600 pi, since you got to give me that decimal? 600 pi is obviously a little something I like to call 1884.956. And again, since this is the rate of change of volume, it's going to be cubic inches per minute. So, like that. I'll put a box around that guy too. But there you go. There's another one done. Let's do 21. 21 says sand is being dropped at the rate of 10 cubic feet per minute into a conical pile. If the height of the pile is always twice the base, at what rate is the height changing when the pile is 8 feet high? All right, so again, they're giving you dV dt right off the bat. And again, they're talking about dropping sand off of wherever it's being dropped from. But again, this question is about the cone of sand that's forming. So for us, dV dt wants to be a positive 10 for sure, not a negative 10. The height of the pile is always twice the base. Okay, that's interesting to know. I guess that means that if I took the height and divided it by the radius, then the height is always twice the radius. So that would put us in a ratio of 2 to 1, right? Or put another way, it just means that the height is equal to the radius times 2. So there's your conversion factor. And that's great. So what else do we know? At what rate is the height changing? Means we're looking for dH dt, which that's getting a little boring now. We probably need to start talking about the radius eventually. But it says when the pile is 8 feet high. So they're also giving you h, telling you that it's 8. So this is pretty similar to the previous problems where we've got the same 3 pieces of information. We're just shuffling them around again. So volume equals 1/3 pi r squared times height. But again, we want to replace r to get everything in terms of h. So the h equals 2r is not the conversion factor I want. I want to actually divide by 2 or multiply by a half. But I want the conversion factor that says half of h is equal to r, so that I can come back up here and replace the r with 1/2 of h. That'll get squared times by h. That'll need a pi. I'll also need a 1/3. But there's everything. So clean this up. This will be 1/4 times 3 is 1/12 times pi times an h, that is cubed. Now we differentiate. And we find that dV dt has to equal 1/4 times pi times an h, that is squared, times a dH dt. And so if I'm trying to find dH dt, then just leave this guy alone. That'll be your variable. Substitute everything else. So the rate of change of the volume is 10. 1/4 is 1/4. Pi is pi. H we know is 8. So square that. And then just leave dH dt as your variable. So what's this going to be? 8 squared is 64, but 64 divided by 4 is 16. So that's a 16 pi. So we've got a 10 that equals 16 pi times dH dt. And again, just divide. So you get 10 over 16 pi. That's going to be the answer to the question. Make sure you reduce that. They're both even, obviously, so you get 5 over 8 pi, which I then want you to put in your calculator. And 5 divided by 8 pi. I forgot the parentheses. 0.199. And since this is another rate of change of a height, we would want it to be just in plain old feet per minute. So not square feet, not cubic feet. But there you go. That's our dHdt. So there's another problem. Next. 22. Water is pouring out of a conical funnel of radius 4 and depth 10 at the rate of 3 cubic inches per second. How quickly is the water level changing when the water is 5 inches deep in the funnel? Okay, I mean, this is the same old stuff. Again, we've got this funnel, but we're more concerned about the water in the funnel, which means that the only reason that they told us that the funnel had a radius of 4 and a depth of 10 was so that we could establish that ratio and substitute in for the h and the r. So again, we know that the height of the funnel divided by the radius of the funnel would equal 10 divided by 4, which if you cross reduce tells you that 4 times h equals 10 times r. And what are we solving for? How quickly is the water level changing? So this is another problem where we want to solve for h, which means we would want to replace r. So solve this for r to give us something to substitute into the equation. You get 4h divided by 10, which you better simplify. So it's actually 2h divided by 5 equals r. So there's your conversion factor. Now, what about the water? It says we want to find the rate of change. 3 cubic inches. How quickly is the water level changing when the water level is 5 inches deep? All right. I mean, that's all I need to know. We already decided we don't need the radius. Real quick though, if you did need it, since 5 is half of 10, wouldn't the radius just be half of 4? So it would be 2. So we know the radius, but we don't need the radius because we're going to substitute it right out of our equation anyway. So volume is 1/3 pi r squared h. But like I said, we're immediately going to get rid of r by replacing it with an expression containing h, so the 2/5 h goes right in. And now we're all h's all the time. So what is this? 4/25, aka 4/75 times pi times an h that is cubed. Yeah, works for me. All right, so differentiate that. You're going to land on a dv dt. That equals, let's see, multiply by 3, and that'll reduce down to 4/25 times pi times h squared times dh dt. And you should be finding yourself in a familiar position where you know all this stuff. I never actually did it, so I guess I'll do it. But what's it say? It says we are losing volume at a rate of 3 cubic inches per second. So dv dt will be negative this time, -3. How quickly is the water level changing? That means again we're looking for dH dt. So that guy's our big old question mark. And it says when the water is 5 inches deep. That's them telling us that the height is 5. And again, r, we don't care. And dr dt, we don't care. And even the volume, we don't care. Okay, all of those unknowns don't really matter to us because of how we set up our equation. So let's just do it. We want dv dt to be -3. Then we want this 4/25. We want a pi. H is 5. So in goes 5 squared. Then dH dt. And then we got it off a little bit easy here again because 5 squared is 25, which will immediately cancel with that 25 in our denominator. So we've got -3 equals, now is this a 9 or a 4? It's 4, because remember up here it was a 4. So again, this is just my writing tablet being a little bit weird. That's supposed to be a 4. Don't freak out. So where were we? We just have a 4 and a pi because everything else canceled. So that must mean that the rate of change of the height is negative 3 divided by 4 pi, which of course is approximately worth, I don't know, negative 3 divided by 4 pi. Negative 0.239. And finally, don't forget your units. We see up here that we're working in terms of inches and we're working in terms of seconds. So since this is height, you will stick to just plain old inches every second. And I guess that's kind of crammed in next to my face, but that's okay. So there's that one. That's another one down. How many more are there? 23, 24, 25, 20? I don't really feel like doing all these. Do you guys really need me to? All right, I will. I might go silent mode though. I don't feel like narrating this anymore. Okay, fine, I will. So we got another right circular cylinder. Radius is 4. Height is 10. And an axis, vertical, and vertex down. All right, that just means that you draw it the way I drew it. Water is being pumped into the tank. So that means we're starting with only a little bit of water, and they're pumping more in. So obviously the rate of change of the volume is a positive number. We're gaining more and more. So dV dt is positive 9. At what rate is, oh my god, it's height again? It's really got to be radius one of these days. All right, but it says at what rate is the height? So we're looking for dH dt, just like we were for every other problem. When the water is 8 feet deep, and that's them giving us h again, which means this problem is actually pretty easy. Again, we've got kind of everything we need. So the only thing we don't have yet is that conversion factor that's going to allow us to substitute in for r. So again, our formula, volume equals 1/3 pi r squared h. This formula is no good, not with an r and an h in it, because that r, we don't have any information about r, so we need it to go. So here's the one piece of information we do know about r. We know that if we did the ratio of h to r, that ratio is always going to be 10 to 4, no matter what. And I could go ahead and reduce that right now. This is really a ratio of 5 to 2. Then I can cross multiply to find that 2 times h always equals 5 times r. And again, we want to substitute in for r to make it go away. So that means solving for r by dividing. So we get 2/5 of h is the same as r. So we then take that expression and plop it in where the r used to be. So we've now got a v that equals 1/3 times pi times 2/5 h squared times h. That's it. So again, I would clean this up and then I would differentiate. So squaring this gives me 4/25 times 3 is 4/75. Didn't we just have that? Yeah, we just had that. That's annoying, but whatever. All right, then we get a pi and then we get an h cubed. So again, just differentiate, substitute, get an answer. So this is going to be a dV dt that equals 4/25 times pi times h squared times dH dt. Okay, so substituting in dV dt we know is 9. Then you've got a 4/25 times a pi times an h that is equal to 8 times a dH dt. All right, so here the numbers are a little uglier because this time for sure I'm getting 8 squared, which is 64. That's not going to cancel with this 25 at all. So we just have to do 64 times 4. And I don't actually, I could do that in my head. 256. Seems like it's 256. Look at Mr. F go. So this is 9 equals 256 over 25. And that doesn't reduce because the only factors of 25 are 5 and 5. That's not going to reduce a 256. So that's times pi. And this is dHdt. Alright, so the good news is we solved this pretty easily. Don't imagine dividing by all this. Imagine multiplying by the reciprocal instead. And that should seem easier. So 9 25s are 225. That feels low. I'm going to double check that answer, but I think that's right. So this will end up giving you 225 pi divided by 256, because remember we multiplied by the reciprocal, and that got us dHdt all alone. So nothing left to do but make this a decimal. So 225 pi. Did I just screw up? Of course I did. That's my bad. So this pi that we had here, he's technically in the numerator. So when I multiply by the reciprocal, that pi, of course, is going to end up in our denominator down there. So really our answer is 225 over 256 pi, which is giving 256 pi. Feels a whole heck of a lot like 0.280 technically. It's 0 point, oh man. Oh, good. 0.2797. So 9s are kind of annoying, but if you want to round to 3 decimal places, then obviously the 9 rounds up and it becomes essentially a 10. So that goes to 280. So give me the 280 and don't chop the 0 off the end. That becomes a significant digit. Make sure you keep it. And this is height again. So I guess it's feet per minute. But there you go. Again, I got to have the 225 over 256 pi. And then I got to have the appropriately rounded decimal. So that's 23. Let's do 24. All right. Looking at this problem, I just don't think I'm doing it. Because it's asking for the height again. There's nothing different here. I'm not doing it. If you guys want an answer, you better ask for me to do it in class. 25, are you better? It says, how fast is the altitude changing? So, no, this one's not better. I'm not doing it. It's a little different because it says the altitude is always 1/4 of the diameter. So I'll be happy to walk you through that part, I guess. But what does that mean? Again, they're just telling you sand is pouring from a pipe and it's making a cone. So draw yourself a cone. What does it say? The altitude is 1/4 of the diameter. So you know what? Let's make the diameter way bigger. We'll make this big old diameter. And if that's my diameter, then my height is supposed to be 1/4 of this. So my height is barely anything at all. So we've got this really pretty squat little cone like this. But again, what did we just say? We said the altitude, the height, is always equal to 1/4 of the diameter. But remember, we don't care about the diameter. We want the ratio of the height and the radius. So that means the height is always equal to 1/4 of, what's the diameter now? Isn't that 2 times the radius? And if you put that over 1, then you see that that's giving 2/4, aka 1/2 of the radius. So there's your little conversion factor. Your conversion factor would be that the height is equal to 1/2 of the radius. But again, every single one of the problems on this worksheet, and I'm going to have to change this for next year, but they all are about the altitude, which means you don't want to solve for r. r, or you don't want to solve for h, you want to solve for r so that you can substitute. But obviously just multiply through by 2. And you'll find that this time your r in your equation, you'll just set it equal to 2h and go from there. And 25 will be just like every other problem from there. I think if something's different, ask me in class. 26. Oh my god. And what rate does the level of the water? Guess what that is? That's dH dt. And guess what that means? It means I'm not doing this problem again because it's the same. I guess I will say the part B is weird. Part B says when the cup is half full. Well, in a paper cup that's 6 inches deep, I'm sure a lot of you probably thought that that meant that when the height was 3, that was half full. But pretty obviously, doesn't half mean when you've cut two things equally into two parts? Obviously the top half of a cone is way bigger than the bottom quote unquote half. So the 3-inch mark is not the halfway mark. You'd have to actually solve for the volume, figure out what the volume is. Let's just pretend it's 100 pi. So obviously half of the volume would be 50 pi. Then you'd have to set up the whole equation all over again. Set the volume equal to 50 pi. And then figure out what height delivers that 50 pi. I just don't care about this. I don't care about having you guys do that geometry problem of figuring out the dimensions, where the radius and where the height would be the sweet spot to give you half of the volume of the cone. Don't sweat that. I don't care about it. Make sure you can do the other part though. 27. Oh, good. We're finally done. Yay. I'm done. I'm not doing more. Again, ask me in class if you have any questions. Okay, bye.